Hello students, welcome to OrganiChemVerse YouTube channel. In this video, I'm going to explain about the two famous reducing reagents in organic chemistry, that is sodium borohydride and lithium aluminium hydride. Many students often they get confused between these two reagents. They don't know what their reactions are. So in this video, I'm going to clarify what is sodium borohydride. It is a mild reducing reagent with the molecular formula NaBH₄. What is lithium aluminium hydride? It is a strong reducing reagent with the molecular formula LiAlH₄. What is the choice of the solvent when we use these reagents? Whenever we use sodium borohydride, mostly we are going to use a protic solvent like methanol, ethanol, or even water. That means it's reactive even in these protic solvents. Of course, you can use aprotic solvents. There's no problem, all right? But whenever we use lithium aluminium hydride, we can't use the protic solvents because lithium aluminium hydride is a strong reducing agent. It's very, very reactive. Therefore, we can't use protic solvents, hence we have to use a protic solvent. What is the best example for a protic solvent? Tetrahydrofuran. What about the reaction? Sodium borohydride is a mild reducing reagent, right? And it is selective. What about lithium aluminium hydride? It is a strong reducing reagent and it is non-selective. What do you mean by non-selective? That means it will react with almost all of the functional groups. So let's see the reaction, right? So when you use sodium borohydride, you are going to get a reduced product, that is primary alcohol. You can even do the reaction with ketone. So you are going to get a secondary alcohol. By default, you are going to get primary and secondary alcohol respectively. But whenever we use lithium aluminium hydride, along with these two reactions, remember students, lithium aluminium hydride does these two reactions as well. Okay. Can also reduce carboxylic acid to alcohol, primary alcohol. It can even react with an ester. It can react with an ester and it can reduce it to an alcohol. It can even reduce nitrile cyano compounds to the corresponding amines. Not just that, it can even reduce amides. What are amides? CONH2 to form a primary amine. These are the major difference. These reactions cannot be done by sodium borohydride, whereas lithium aluminium hydride along with an aldehyde and ketone, it can also react with the acid, ester, nitrile and amide to form the corresponding products. Now that you have learned the reactivities of sodium borohydride and lithium aluminium hydride, let's apply the concept on some of the questions. The first question is finding out what are the products A and B when the given molecule reacts with sodium borohydride and lithium aluminium hydride. Sodium borohydride is a selective reducing reagent, therefore it's going to reduce only the ketone to secondary alcohol. So what product are we going to get? The ester will remain as it is. Only this part is going to get reduced to secondary alcohol. So this should be our product A. Just check in the given options where do we have it. So here you see the ester is reduced, so not possible. Look at the option B. So this could be the correct option because A is correct. But let's check for option C. You see that only the carboxyl part is reduced. This is not possible as these are not stable. So you can eliminate option C. And what about D? You can see the ester is reduced, ketone is retained, which is not possible. Hence, you can eliminate this. Therefore, the correct option is option B. However, let's check for lithium aluminium hydride. Since it is a strong reducing reagent, first it will convert this ketone to the secondary alcohol. It will remain like this. And then what happens to this ester? First, the hydride will attack here and open up the ring. That means here we are going to get OH. And here we will have an aldehyde. Aldehyde further will get reduced to form a primary alcohol like this. So this is our product B. And you can see the structure given here matches with what we have written. Hence, the answer is option B. I have taken this question specifically in order to compare the reactivity of these two reagents with the same reactant molecule. In the question, you have to identify the reaction which is not correct. Let's check for option A. So there is a carboxylic acid. It is treated with thionyl chloride. So it's a chlorinating reagent. It will convert the carboxylic acid to acid chloride. The byproducts are gases, sulfur dioxide and HCl. They will escape from the reaction mixture. That's why this is the most ideal method to convert carboxylic acid to acid chloride. Since the reactive center is over here, the double bond will not be changed. It will remain as it is. Therefore, this is a correct reaction. There's nothing wrong with this reaction. So this cannot be our answer. Let's check for option B. There is a carboxylic acid and it is unsaturated. That means there is a double bond. Is it conjugated with respect to carboxylic acid? No, because if this is a functional group, this is alpha carbon, this is beta, and this is gamma carbon. So it is beta gamma unsaturated. That means it is isolated double bond. When do you call it as conjugated? You can see that at alpha and beta, there is a double bond. So we call this as alpha beta unsaturated carboxylic acid, and this is not isolated. This is conjugated. What about this isolated? Why am I explaining this? Because whenever you have conjugated double bond like this, and when you treat this with a strong reducing reagent like lithium aluminum hydride, then this double bond will also get reduced and the carboxylic acid will reduce to alcohol. Therefore, the resultant product will be this. But in this case, since it is isolated, it will remain as it is. And what happens to the carboxylic acid? It will convert to primary alcohol. So remember, the lithium aluminum hydride cannot reduce the carbon-carbon double bond. When it is attached to the carboxylic acid, only then it will get reduced. In case of this, it is isolated, hence it will remain as it is. So this is a correct reaction. There is nothing wrong with this as well. Hence, this cannot be our answer. Let's check for option C. Sodium borohydride is a weak reducing reagent. It can reduce only aldehydes and ketones. It will not reduce carboxylic acid. Therefore, this is an incorrect reaction because in the product they have given alcohol, so which is not correct. And remember, what will happen when you add sodium borohydride and there is an acid in the molecule? They will get react with each other because there is H plus here and hydride will form H minus. Therefore, what happens? They will neutralize each other. Therefore, this reaction is not favored. The incorrect reaction is as shown in option C. The reaction given in option D is correct. How so? It is a Grignard reagent. When it is treated with carbon dioxide, you see that this carbanion will attack this carbon and it's going to form a carboxylate salt. Upon hydrolysis, we are going to get the corresponding carboxylic acid. Therefore, the incorrect reaction is as shown in option C. In this question, you have to find out the correct reaction sequence. The first molecule is para-nitrobenzaldehyde. It is treated with lithium aluminum hydride. Here you can see that the aldehyde will get reduced to alcohol. Since it is a strong reducing reagent, it can convert the nitro to NH2. Therefore, this is not correct. The aldehyde is as it is. Hence, this is wrong. Let's check the second reaction. An ester will get reduced to primary alcohol when we treat it with lithium aluminum hydride. And aldehyde, as I just told you, it will also get reduced to primary alcohol. So, this is correct. So wherever we have option B, that could be the answer. So it could be either A, C or D. Let's check for other reactions. So this is an ester and you see this is a weak reducing reagent. That means what? The ester should remain as it is and what about the ketone? Should convert to secondary alcohol. So this is also correct. Let's check the last reaction. Will sodium borohydride convert nitrobenzene to aniline? No, not possible because this is weak reducing reagent. So D cannot be the answer. So what two reactions are correct here? B and C. So which is the correct option now? Option C. In this question, you have to match the given reducing reagents with respect to their reactions. Certain reactions can be carried out by more than one reagent, so you can match that as well. In the first reaction, you can see there is an ester and ketone and it is reduced to alcohol and the ester is remaining as it is. That means what? We use sodium borohydride. So for the first reaction, for reaction A, we use specifically R as the ester is remaining as it is. Let's check for B. What is B here? You see that the ketone is reduced to alcohol. That means it could be either sodium borohydride or lithium aluminum hydride, but not zinc amalgam in HCl and red phosphorus in hydrogen iodide, because these are very strong reducing reagent. They will completely remove the oxygens. Okay, you have to remember that. And you see the bromine is also removed. That means what? The hydride is displacing this bromine. That means it has to be a strong reducing reagent. And what is that? That is lithium aluminum hydride. So B is matching with Q. Now let's check for C. The ketone is reduced to alcohol. So either it has to be sodium borohydride or lithium aluminum hydride. But look at this double bond. It is in conjugation with the phenyl group, right? It is not isolated. That means what? It can undergo resonance with the pi electron cloud present in the benzene. That means what? This will also get reduced, means it is lithium aluminum hydride. So C is also matching with Q. Here, there is no rule that a particular reaction should match with only one reagent. As I mentioned earlier, the reagent can repeat and there could be more than one reagent for a particular reaction also. Now let's check for the last reaction. You see here, the ketone is completely reduced to CH2 and the CO here, which is a ketone, is also getting reduced completely to the hydrocarbon. And what reagents do this? As I just explained to you, zinc amalgam in HCl, nothing but Clemmensen reduction, and red phosphorus in hydroiodic acid. Remember, this is a strong reducing reagent which will reduce alcohol aldehyde ketones to their corresponding hydrocarbon. So D will match with P as well as S. So I have used different reducing reagents in order to compare their reactivity with respect to different functional groups. For the last question, you have to identify the incorrect statement from the given options. The order of reaction by lithium aluminum hydride and that of the reduction by sodium borohydride each is 2. Is this a correct statement? Yes, it is. How so? Because whenever an aldehyde or a ketone reacts with lithium aluminum hydride, the rate law can be expressed as R is equal to K multiplied by whatever is the substrate. Either it could be an aldehyde or ketone and the lithium aluminum hydride. With respect to aldehyde or ketone, it will be first order reaction, and same with respect to this reducing reagent. So what will be the overall reaction order? It will be 2. Similarly, for sodium borohydride also you can write like this, because which will be the rate determining step here? The rate determining step will be the attack of the hydride, either from sodium borohydride, lithium hydride, doesn't matter. It is going to attack the carbonyl, and this is the slowest step, and that is the rate determining. So both of them are involved in the rate law. Hence, the order of the reduction reaction for both the reagents would be 2. Therefore, this is a correct statement. Now let's check for option B. Aluminium hydrogen bond is more ionic than boron hydrogen bond. Hence, lithium aluminum hydride can produce larger concentration of the hydride ion than that of sodium borohydride. This is absolutely correct. So since the aluminium hydrogen bond is more ionic, you can see that the hydride ions will be formed easily. Hence, will be stronger reducing reagent as compared to sodium borohydride. Therefore, this is also a correct statement. Let's check for the option C. Lithium aluminum hydride cannot reduce nitro group. This is a wrong statement, because lithium aluminum hydride can reduce nitro groups, but the outcome depends heavily on whether the nitro group is aliphatic or aromatic. So that is not specified here. So straight away you can say that this is the incorrect statement. We can check for option D as well. In spite of very small rate constant of the reduction of any carbonyl function other than aldehydes and ketone, the rate of reduction with lithium aluminum hydride becomes appreciable due to large concentration of hydride ion. This is correct. This is something which is explained by the option B. So which is the incorrect statement here? Option C. So these are some of the examples from the sodium borohydride and lithium aluminum hydride, the selectivity reaction, etc. I have given some more questions at the end of this video. Please do solve them and please do comment your answers in the comment section and don't forget to subscribe the channel. Thank you.